Welcome to this lecture. My name is Mark Scythian. The date today is November 3rd, 2025. So if you're working on equilibrium and statics problems for your physics homework, stay tuned and we are going to solve 5 fundamental equilibrium and statics problems. The first one is this picture is hanging by 2 tension wires at some angle to the vertical. The following picture is hanging on a wall. Use trigonometric functions to determine the weight of the picture. So the first thing we have to do is determine where the resultant is as the 2 wires make their angle of tension force in the diagonal upward direction to hold the picture up. We need to know what that resultant value is. So based on what we have in the problem, we know the individual force tension for each diagonal wire is 30 newtons of force. So this then creates the following right triangle with respect to the left side here. This is replicating the triangle on the left. We'll choose this triangle. And we know based on a 45-degree angle from the horizontal, we have only 45 degrees left to then ascertain the correct angle projecting to the opposite side, and then the right angle made is the adjacent side, and then the diagonal side is the hypotenuse. So if we know the rules for trigonometry with respect to dealing with, in this case, the 30 newtons of force on the hypotenuse side, we can pick the resultant A is what we want. So those 2 legs, the hypotenuse and adjacent, are relevant, whereas the opposite leg is not. So cosine is the ratio of adjacent side divided into hypotenuse. Sine is opposite over hypotenuse, and tangent is opposite over adjacent. So we'll just work with cosine because that's all we need. We take the cosine of this angle, 45 degrees, and we make it equal to our adjacent side, which is what we want to calculate, divided into what we know, hypotenuse side 30 newtons. So in this case, using algebra, we can simply just multiply the cosine 45 degrees times the 30 newtons to equal the adjacent side, or the numerator. So we calculate 21.2 newtons force total. So if we were to multiply that value times 2 to represent 2 cables, we would then calculate the total resultant upward force, which is equal to the weight of the picture. So the final answer is 42.4 newtons force for weight of picture, or 9.5 pounds force. There are 4.45 newtons force to 1 pound of force. Moving on to number 2. The sign below hangs outside the physics classroom, advertising the most important truth to be found inside. The sign is supported by a diagonal cable and a rigid horizontal bar. If the sign has a mass of 50 kilograms, then determine the tension in the diagonal cable that supports its weight. So in this scenario, we have to first find the equivalence. So first, the sign has a mass of 50 kilograms. But we know force weight is the mass times gravity, so we multiply the 50 kilograms times gravitational acceleration. On Earth, this is 9.81 meters per second squared. We calculate a force newtons weight value of 490.5 newtons force. So the corresponding weight side would actually be, in this case, the opposite side, projecting from the angle. So we have to place a reference in there to correspond that particular resultant vector, but now we're reversing it into the cable tension based on the rigid horizontal bar. So we got 30-degree angle, we're projecting an opposite angle with a value of 490.5 newtons force, weight. So now we can set up the sides. Opposite is the force weight. Then the adjacent leg is the horizontal bar. And then it connects with the hypotenuse diagonal. So in this case, what is relevant? The opposite side and the hypotenuse. We need to know the value of H, which is equal to the tension in the cable. So sine is opposite over hypotenuse. So we divide 450.5 newtons into H. So then we can equal the sine of 30 degrees into the ratio of 490.5 over H. So all we have to do is just swap the H to equal 490.5 divided into the sine of 30. So the sine of 30 is 0.5, so when we divide 490.5 into 0.5, we got 981 newtons of force for the cable, which is also equal to 220.4 pounds force, 4.45 newtons of force to 1 pound of force. So next we move on to problem number 3. The following sign can be found in Glenview. The sign has a mass of 50 kilograms. Determine the tension in the cables. So again, we can draw a bit of a free body diagram and isolate the mass into weight of the sign. So we calculate 490.5 newtons of force weight is equal to the sign based on force weight is equal to mass times gravity. So then if we isolate the vector points, we basically have two triangles that yield the following diagram here. And because it's 45 degrees from the horizontal, and those are two 90-degree angles, all that's left is the 45 degrees on the inside. So to figure out the opposite side, that is just a projection of the opposite leg of the angle here. And then we know all diagonals are always hypotenuse, so then we're left with just this right angle for adjacent. So what is relevant if we just pick one triangle? Adjacent, and then we need to know the tension of this cable here, so that is the hypotenuse. Adjacent and hypotenuse. So AH, A divided into H, that's cosine. And the same process, once again, we'll just flip these around. So we get 693.7 newtons of force total divided into two cables. So each cable has 346.87. We'll round it to 347 newtons of force, which is equal to 78 pounds force per cable, or 347 newtons force per cable. Moving on to number 4. So number 4, after its most recent delivery, the infamous stork announces the good news. If the sign has a mass of 10 kilograms, then what is the tensional force in each cable? Use trigonometric functions and a sketch to assist in the solution. So again, we draw a bit of a free body diagram just to isolate the center of mass times gravity. So in this case, the sign has a weight of 98.1 newtons force. So that's based on force weight is equal to mass times gravity. So we enter that in and do the same process. We just draw a repeat diagram. And now we have two 30, 60, 90 triangles. So we can isolate one of the sides because these are 60-degree outboard angles. One 90 degrees, that leaves just 30 because all triangles have 180 degrees. So again, opposite side, isolated, hypotenuse, adjacent. So what is relevant? We need the hypotenuse, and we have the adjacent side value. We have the opposite side value I meant. So if we look at the vertical as the opposite side, 98.1 newtons, that's relevant. And then we need the diagonal cable tension value, so that's a hypotenuse, and then the adjacent side is irrelevant, is what I meant to say. So what does that leave us with? Hypotenuse and opposite. So OH, O divided into H, that's sine. Sine of 60 degrees is equal to 98.1 newtons force divided into H, so we just swap these around. Get 113.3 newtons force, then divided into two cables. So we round that to 56.7 newtons force per cable, or 12.7 pounds force per cable. So moving on to the last problem. Suppose that a student pulls with two large forces, F1 and F2, in order to lift a 1 kilogram book by two cables. If the cables make a 1 degree angle with the horizontal, then what is the tension in the cable, or in each cable? So again, we can isolate the 1 kilogram mass, calculate its force weight, 9.81 newtons force weight, based on force weight is equal to mass times gravity. Then we can isolate the triangle it makes. Can zoom this up, and we'll pick one of the triangles, the right one in this case. So we have our 9.81 newtons force weight object. In this case, it's a 1 kilogram mass book, which is 9.81 newtons of force weight. So we've isolated the weight of the book on the opposite side. And we need to know the hypotenuse, or the diagonal cable tension. So that leaves us with opposite and hypotenuse. So again, that's SOH sine is opposite over hypotenuse, cosine is AH, adjacent over hypotenuse, and tangent is OA, opposite over adjacent. So we substitute the information in. Opposite side is 9.81 Newton's force divided into hypotenuse h. And again, we just swap this around. We get 562.1 Newton's force total divided into two cables. So that's 281 Newton's force per cable, or 63.1 pounds force per cable. Thank you for watching this lecture and have a great day.